we are ultimately trying to prove the Gaussian integral. That is, the integral of the Gaussian function f of x equals e to the negative x squared over the positive real line. The Gaussian integral has many applications, with its most significant being, with a slight change of variables, it's used to compute the normalizing constant of a normal distribution.
Oh, that's okay. That's fine.
We have chosen to solve this
That's alright, just leave it, it's fine.
using multivariate calculus and polar coordinates with a Jacobian determinant. The first step of this procedure is to solve the following equation 1, involving the gamma function I shown at the top of the slide, which is an extension of the factorial function to complex numbers. To do this, we will first evaluate the numerator using a double integral, since the two integrals I of m and I of n involve different variables. This is particularly useful here as we are now able to switch to polar coordinates and can exploit the trigonometric identity sin squared theta plus cos squared theta equals 1.
Okay, so let x equal r sine theta and y equal r cos theta. So next we need to consider the limits for the new double integral. Since x and y are positive, that means that x and y are in the first quadrant, therefore theta is between 0 and pi and 2. Also, both x and y are positive, therefore r also has to be positive. Thus r is between 0 and infinity, as r is unbounded by a finite number. Okay, so next we need to consider the dx dy in the new double integral. We can calculate this by using the Jacobian determinant, which is used when changing variables and calculating double integrals. So, for j, we're getting a matrix with derivatives, and after a couple of lines of working, we get the dx dy is equal to 2r sine theta cos theta. So now we can input our new dx dy, which is of course r sine theta cos theta, as well as our new limits into our double integral. After a couple of lines of simplifying the double integral, we get it being equal to the integral from 0 to infinity of r to the power of m plus n minus 1 times by e to the power of negative r, which is multiplied by the integral of sine theta to the 2m minus 1 times by cos theta to the 2n minus 1, which is of course integrated from 0 to pi and 2. So note that we can split the double integral into the multiplication of two integrals, as both integrals are in respect to different variables.
Because r to the n plus n minus 1 e to the negative r integraled infinite to 0 is equivalent to the function I to the n plus n. This allows us to simplify the equation of the first line to I n plus n times 2 integral pi over 2 sine theta to the minus 2m minus 1 cos theta 2n minus 1. This is also therefore equivalent to the function im. This then allows us to change the equation of the first line to im times in over im plus n. We now have the original equation and can therefore be proven by setting m and n to 1 to 0.5. We could then simplify the equation to the fourth line. This will then change the equation to I to the half squared over I1 equals to 2 pi on 2 integraled sine theta to the negative 2n minus 1 cos theta to the 2n minus 1. Because the property of the Gaussian property involves I to the n plus 1 equals to n minus 1 factorial for n subset of all natural numbers. Basically meaning, essentially for all whole numbers, it is equivalent to a factorial.
As we have I half equaling to the square root of pi, let's look at trying to get Ix into a similar form of the Gaussian integral. Here we have Im equals to the integral bounded between 0 and infinity with functions x to the power of m minus 1 times e to the power of minus x dx. By using integration by substitution, we will let x equal to u squared, and thus to make u the subject, u equals to the square root of x. Afterwards, we differentiate with respect to u to get dx equals 2u du, which we can then sub u equals to x to the power of half to get 2x to the power of half du. We can therefore sub these into our first equation to get Im equals to the integral between 0 and infinity of u squared to the power of m minus 1 times e to the power of minus u squared times 2u du. After moving the 2 to the front of the integral and timesing the u's, we get 2 times integral of function u to the power of 2m minus 1 times e to the power of minus u squared du. Now in order to get rid of the u multiple, we set 2m minus 1 equals to 0, so m equals half. Following this, we get im half equals 2 integral between 0 and infinity with function e to the power of minus 2 squared du. Therefore, to make the integral the subject, we divide 2 to both sides to get half times I half, which equals to root pi over 2, thus proving the Gaussian integral.
Okay, just in case it wasn't clear, the I just referred to the gamma.
Yeah, no, that's fine. It was clear. I'm glad that you said that, but I know what you're talking about.
Okay.